So the guy in this book calls them story problems. To be honest, I feel like he's just showing his age. Nobody calls them story problems anymore. We call them word problems now. But when I was growing up, that's what they're called, story problems.
When did we start calling them word problems?
I don't know. Sometime in my teaching career, that's when it started. But it was story problems when I started, and now it's not. It doesn't matter. They're the same problems, okay? So, here's what's going on in related rates problem. We're going to find the rate. We have two different quantities. We're going to find the rate of change of both of them, but it's always going to be with respect to time. Okay, so we're going to take the derivative with respect to time of quantity A, and we're going to compare it to the derivative of quantity B with respect to time, and we're going to see what's happening to those quantities during that time, right? They're going to be increasing, they're going to be decreasing, and we're trying to get a sense of how fast or how slow those kinds of things are changing with respect to time, and then get a comparison to each other, okay? The key thing is those quantities have a relationship in some way. That's why it's called related rates. They're not just random, they aren't just two random quantities. They have to have some type of relationship. Okay. So I'm going to give you, like I said, I'm going to give you a bunch of steps. Write as much of it down as you think you need. This should be reviewed, but at the same time, maybe seeing it a little differently, and maybe that would be helpful to you. Okay. So first thing you're going to do is, if you aren't given a picture, you definitely should draw a picture. I know you guys don't always like to do sort of, it takes up too much space and that kind of thing, or you don't like your drawing or whatever. Okay, it doesn't have to be perfect. I just often think it can be really helpful to see it. If you can see what's happening, and then at the same time, from my perspective, if you've drawn a bad picture, and I don't mean bad from an artistic perspective, I mean that the information in the problem doesn't match your picture, that will help me help you figure out how to get that going the right way, okay? Choose your variables if they aren't chosen for you. A lot of times they will be chosen for you. And you don't have to be creative with that. If you want to just always have them as X and Y, great. Make them X and Y, I don't care. Doesn't matter, okay? Then, of course, write what's given and what is to be found. And when you're taking the derivative, in this case, we are going to use the d over dt, okay, of whatever dx over dt, dy over dt, whatever you choose your variable to be over dt, because we are finding with respect to time. Good start. All right, number 3, write an equation. Easy enough. Once you've figured out what your variables are going to be and what they all mean, you're going to write an equation. You're going to have your sort of normal equation, right, with your x's and y's, or your whatever your variables are going to be. Now, here's the thing. I'm going to give you some subheadings from this. Okay, the first one is, of course, if it's a changing quantity, that's telling you use a variable. And so you have to be able to analyze the situation, go, okay, I've drawn my picture, I've established what my variables are. Are those variables changing, or are they staying the same? With respect to time. Over time, are they going to change or stay the same? If they're going to change over time, then you have to use a variable there. If over time they aren't going to change, and that quantity stays the same, then use a number. I mean, a constant, that's just a number, all right? And then this is, again, requires some analysis, but you want to know this too, okay? Look for secondary relationship between the quantities so you can reduce the number of variables. So for example, if right off the bat you're like, oh, there's an A, there's a B, there's a C, maybe C I can write in terms of A. Because of course, eventually we're going to differentiate. And if you have too many derivatives in the problem, maybe you won't be able to find one of them, and then you won't be able to finish the problem. So sometimes you get going in the problem, you're like, wait a minute, I need to know this quantity, or I need to know this derivative, but it's not given to me. How am I supposed to find it? Well, that's when you might go back and go, maybe I shouldn't have used so many variables, or I could have used a variable in a different way because they told me about the relationship between them, okay? So look for that. And sometimes, like I said, sometimes you don't figure that out until after you've done the problem. Switching to the next page, because obviously I've run out of room, I actually have 6 total little steps here, okay? So next page. Implicit differentiation with respect to t. It's always going to be implicit because we're going to be finding the derivative with respect to t, and of course we have other variables that aren't t in the problem. I think at this point we could just say differentiate, but it's related to what we just did, so might as well stick with it. Let's see. Okay. Whenever you have numerical values to substitute, do that. Then you can solve it. And last but not least, this is the part you're gonna, I don't know, maybe you won't like it. Maybe you're used to doing this. It's gotta be a sentence. Gotta be a sentence explaining your answer, what it means. I like to say in my Algebra 2 classes, the problem started off with context, the answer should end up with context. We talk about consistency all the time in math. If the problem has fractions, the answer should have fractions. If the problem has decimals, the answer should have decimals. I get it on the AP exam, that doesn't necessarily matter, but that theme of consistency prevails oftentimes through math, so. Okay, all right, I'm gonna have you turn to your, if you want, you can certainly write down what I'm about to put up here. You can take a picture of it. It's in your book. I should have figured out which page, but it's in the 3-4 section and it is example 2. So if you wanna grab it from your book, it's example 2. You can just screenshot it from there because that's what you're about to see on my screen, is a screenshot of page 62. Thank you. I'll write that down as well. Page 62. And there it is. I darkened in the X and Z so we can see it better. And I did have to look up what a windlass was. I didn't know what that was. It's essentially a winch on a pole. A winch. A winch is it's basically a reel with wire on it that, you know, you've seen them on the front of a Jeep when you're trying to pull stuff.
Like you pull it for the sails.
So,
Like
yeah, there you go. Also, for those of you boat enthusiasts, when you get your boat up onto the, oh my gosh, why did all of a sudden trailer, thank you, wow. You hook the winch up once you get the boat up a little ways, and the winch will bring the boat all the way up to the front of the trailer. Okay. Anyway, here's what's happening in this problem. At this particular situation, there's a winch basically on the top of this pole. They are going to hook this winch to the boat, and they're going to pull the boat in. Okay. The rope is attached at a point 15 feet below the level of the windlass. Okay, so this height difference is 15 feet. So in other words, the pole is like 15. We think of the pole as 15 feet. So here's where we take liberties in math problems. Okay, for example, whenever you have the problem of the kid, looking up at something, they don't mark it from its eyes, they mark it from its feet. It's like you're supposed to be standing on your head. Then they tell you that, right? So like there's probably there's probably some leeway here. The hook where they're hooking it up is probably not exactly 15. The level of the water is probably 15. So we always take some liberties with this problem and we just overlook that. Okay, so don't get too crazy about it. The windlass pulls the rope in at a rate of 30 feet per minute. And so we want to know at what rate the boat is approaching the dock when there's 25 feet of rope out. So here's what we're talking about, just so we're clear. We want to know the instantaneous rate of change when there is exactly 25 foot of rope out. Okay? It is not guaranteed that the rate of change at 20 feet or 15 feet or 10 feet will be the same rate of change. We're not asking about average rate of change. We're talking about at the moment when there is 25 feet of rope out. All right. Go ahead and try this, and then we'll go through it together. So there's a couple things that are going on here. My first thought is I want to label stuff I know, and I at some point this number's already been used, so you should be looking at the numbers going, let's make sure I use them all. Of course, in a lot of these problems, they give you more numbers than you need. That is not the case here. So we'll get to this is a rate. 30 feet per minute is obviously some kind of rate that we're going to use after we differentiate. We want to know what that rate is when the rope is 25 feet out. So what they're telling us is that z equals 25. Okay, 25 feet. That part is important. All right. If you want to talk about 30 and decide what that is, that is the rate at which the length of the rope is changing. Okay, and the question that you have to always ask yourself is that rate forcing that quantity to increase or decrease? And if it's a rate that forces the quantity to increase, then it's going to be positive. If it's a rate that forces that quantity to decrease, then it's going to be negative. So over time, what is happening to z? Is it getting longer or is it getting shorter? So it's decreasing, okay? So what that tells me is that the rate of change of the length of the rope is a negative quantity. That's the key to the whole problem. If you don't make this negative, then you're going to get it wrong. And then, of course, we're trying to find the rate at which the boat is getting closer to the dock, and we don't know what that is. Okay, that's what we're trying to solve. Okay, we're trying to solve for dx/dt. And in most of these problems, most of these related rates problems, you have some geometric or trigonometric formula that you're going to use. Okay, in this case, of course, we're going to have Pythagorean theorem. Oftentimes, these kinds of problems talk about volume of a particular cone or of a semicircle or of a, whatever. So oftentimes you might have to dig up a formula that you aren't used to using all the time. So you got to be careful with that. All right, so in this case, we've got Pythagorean theorem. So I'm just saying that 15 is the y. Of course, you could have put these in a different order. It doesn't matter. And so this is my original formula. We know the length of the rope. The height of the pole is 15. That doesn't change. That is constant. The distance from the dock, the distance of the rope, both of those quantities are going to be changing over time. So then I differentiate. Okay, and of course, actually, there's since we're talking about at the specific time, the instant when the rope is 25 feet, we can find how far away the boat is from the windlass or from the dock at that particular point in time. Okay, and so I went ahead and did that over here. So since we want to know exactly what the distance from the dock is at when the rope is 25 feet, I can just solve this. And I didn't take the time to show my work, but the distance from the dock when the rope is 25 feet out is 20 feet away from the dock. That's going to come into play after we differentiate. So I differentiate, I get 2x dx dt. This is a constant, of course, so it goes away. 2z dz dt. So then I have my x. We found dz dt before. Of course, we want to know exactly when the rope is 25 feet long. And so I can plug those things in, and I color-coded it all nice for you. And so that's where my distance is 25 feet. The rope is 25 feet long. The distance at that point, the boat is 20 feet away from the dock. So now it's just a matter of solving this. Okay. So that's 40. This is negative 1,500. Do the math. Dx dt equals negative 37.5 feet per minute. So that is the rate that the boat is moving toward the dock. Okay. at that particular time. And so my sentence, your sentence should be something like this. When the rope length is 25 feet, the distance between the boat and the dock is decreasing at a rate of 37.5 feet per minute. I don't know why there's an extra period there. Probably because I forced that down. What's important is in your sentence, we don't talk about the positive or negative. We use words like increasing or decreasing, okay? So when we do the conversion from math to English, we want to use the right words.